Hello and welcome back to Adventures in Chemistry with Andrew Elmers. Today we go over Chapter 1 of Modern Chemistry, Matter and Change. Chapter 1. Section 1 is Chemistry is a Physical Science. The objectives of this chapter is define chemistry, list examples of the branches of chemistry, and compare and contrast basic research, applied research, and technological development. Chemistry is a physical science. Chemistry is the study of the composition, structure, and properties of matter and the changes the matter undergoes. More vocab is a chemical. Is any substance that has a definite composition or is used or produced in a chemical process. Chemistry is broken down into 6 branches. There's organic, theoretical, biochemistry, analytical, physical, and inorganic going counterclockwise. The 6 branches are defined as organic is the study of most carbon-containing compounds. Again, the key here is carbon-containing. Inorganic is the study of non-organic substances, many of which have organic fragments bonded to metals. And physical is the study of properties and changes of matter and their relation to energy. Remember, organic has to deal with carbon-containing compounds. And you have analytical chemistry. It's the identification of the components and composition of materials. Biochemistry is the study of substances and processes occurring in living things inside your own body, brain waves and stuff like that. Theoretical is the use of math and computers to understand the principles behind observed chemical behavior and to design and predict properties of new compounds. And this is what drives innovation right here. You have basic research. It's carried out for the sake of increasing knowledge, curiosity, just to learn something new every day. And then you have applied research. It's carried out to solve practical problems in society. Something is a problem, it needs a solution, it's solved by applied research. Technological development involves the use of existing knowledge to make life easier or more convenient. Thomas Edison created a more convenient light bulb after Swan did before him. Again, that's technological development. Section 2, Matter and its Properties. Objectives of this section. Distinguish between the physical and chemical properties of matter. Classify changes of matter as physical or chemical. Explain the gas, liquid, and solid states in terms of particles. Explain the law of conservation of energy as it applies to changes of matter. And distinguish between a mixture and pure substance. Matter is anything that has mass and takes up space. Volume, that's a basic definition for it. Now, mass is a measure of the amount of stuff or material the object contains. Just about everything has mass, so just about everything has matter. I really can't think of an example of something that does not have mass. Now, do not confuse mass with weight. Weight is a measure of the force of gravity upon a person. It's measured in pounds usually. A book on Earth has a different weight than it does on the moon, than it does on Jupiter, than it does on Uranus. However, mass stays the same. The fundamental building blocks of matter are atoms and elements. Atoms are the smallest units of an element that maintains the chemical identity of that element. Atom is well known throughout science, basic elementary, but again, it's a proton, neutron, an electron floating out in orbit around the nucleus over there. And then you have elements, are pure substances that cannot be broken down into simple, stable substances is made of one type of atom, the same type of atom. Now, a compound are made from 2 or more elements in fixed proportion. Over here, you have NaCl, salt. You have one element of sodium and one element of chlorine. It's fixed proportions, 1 to 1. Over here you have another compound. Again, fixed proportions is the key. You have this ways to describe matter. They are properties used to describe matter can be classified as extensive or intensive. Extensive depends on the amount of matter in the sample. It's mass, volume, calories. And intensive depends on the type of matter, not the amount present. This includes hardness, density, and boiling point. All substances have characteristic properties that enable chemists to tell the substances apart and to separate the substances. These are broken down into physical and chemical properties. Physical property is a property that can be observed and measured without changing the material's composition and identity. Examples of this include color, hardness, freezing point, and boiling point. And you also have chemical properties, property that can only be observed through changes that transform the substance into a different substance. Examples of this include the ability to burn, to decompose, fermenting, and reacting with, etc., etc. And now another part of this section are the states of matter. Another objective. Solid is matter that cannot flow. It has a definite shape and has a definite volume. Particles do not flow over one another. Liquid, the particles do flow over one another. It has a definite volume, but it does not have a definite shape. It takes the shape of its container. And gas is a substance without definite volume or shape and flows over the other particles within it. A vapor is an offshoot of gas. It is a substance that is currently gas, but normally is a liquid or solid at room temperature. So I call it water vapor and not water gas. A little chart here to help remember the states of matter and their properties. Solid has definite volume, has definite shape. Liquid has definite volume, but does not have definite shape. And gas has neither. When you increase the temperature, solid has a small expansion, liquid has a small expansion, but gas has a large expansion. When you increase the temperature around it, it will compress. When you put pressure on it, solid will not, liquids will not, but gas will. When we put pressure on it. Now there is a fourth state of matter that's commonly not found on Earth in nature. It's formed at high temperatures, very high temperatures. It's an ionized phase of matter as found in the sun. It's very complicated. You don't find it very often. Now, as you see in this diagram, solid is changed to liquid as you add heat, and which is changed to the gas, which is changed into plasma. And now this picture over here shows the particle composition of the three states of matter in this crystal. In the solid, the particles of the solid has the definite shape, has a definite volume. It's a rigid structure. They vibrate very slowly. They stay in one position, the atoms. In the liquid, it has a definite volume. It only goes up to that amount in the Erlenmeyer flask up here, but it takes the shape of its container, as you can see over here. Where the particles in this flow over one another, which is why you can pour a glass of water. Now, in a gas, particles have free range to move about the cabin, the container they are in. They take the shape and volume of the container. Over here is the bottle, and they bounce off walls, they bounce off each other, and they just move about freely and flow over one another. Now, based off the physical and chemical properties are physical and chemical changes. Physical change is a change in substance that does not involve a change in the identity of that substance. Boiling, melting, cutting, bending, splitting, cracking. Again, is boiled water still water? Yes, of course. It's just now water vapor. These can be reversible or irreversible. A chemical change is a change in which one or more substances are converted into different substances. Now, the identities of the substances change as you go through the chain of the reaction. Now, when you change state from solid to liquid, it's a physical change. Water freezes and becomes ice. Ice melts and becomes water. And water boils and becomes vapor, or water vapor. Now, freezing, melting, and boiling are three of the more common types of changes of state, but there are countless other ways that it can be done. Chemical reactions are chemical changes. It's the same definition. They can be used interchangeably. Chemical reactions include combustion when you burn something and decomposition when you break it down. Over here we see an example of reaction. Methane and two oxygen molecules combine to form carbon dioxide and two water molecules. And then in every chemical reaction you have reactants and products. Reactants is what goes in. Over here, the methane and oxygen. And the products are what comes out. Over here, the carbon dioxide and the water. Now, energy and matter. And this is a fundamental building block of all science. You should pay attention, listen, know this. Energy changes accompany physical and energy changes accompany physical and chemical changes all the time. When you lose heat, when you gain heat, absorbed, released. Chemical and physical changes do not affect the total amount of matter present before and after a reaction. Remember, the amount of matter does not change during a reaction. Also, energy may be released or absorbed, but is never created nor destroyed. This is the law of conservation of energy. It's created by Einstein, I believe, a while back. It's fundamental science. A lot of stuff is based off this right here. And now, the last part of this section is the mixtures and pure substances. A mixture is a physical blend of at least two substances, where each retains its own identity and properties, and they have variable composition. They can be either heterogeneous or homogeneous. Heterogeneous is when the mixture is not uniform in composition. You can think of a chocolate chip cookie, gravel, or soil. Now, homogeneous has the same composition throughout. They're also called solutions. Examples of these include Kool-Aid, air, and salt water. Now, in mixtures, every part of the mixture keeps its own properties. In salt water, the salt and the water keeps its own properties. And a chocolate chip cookie, chocolate chips keep their own properties, and the cookie itself keeps its own properties. A good way to remember the difference between heterogeneous and homogeneous is by the Greek prefix hetero and homo. Homo means the same composition throughout. Hetero means different, a different composition throughout. Now, a pure substance has a fixed composition and differs from a mixture in the following ways. Every sample of a given pure substance has exactly the same characteristic properties. Every sample of a given pure substance has exactly the same composition. Pure substances are always the same, and they are either compounds or elements. And moving on, as you can see in this chart over here, you can start with matter and move your way to a heterogeneous mixture, solutions, compounds, or elements to see how you would describe matter. Section 3, elements. Objectives in this include using the periodic table to name elements and to write the symbols of elements, to describe the arrangement of the periodic table, and to list the characteristics that distinguish metals, nonmetals, and metalloids. Now, an element. Each element has a unique symbol. Oxygen is O, carbon is C, sodium is Na, sulfur is S, hydrogen is H, helium is He, so on and so forth. And the periodic table shows the elements organized by their chemical properties. And the periodic table breaks down elements into groups and periods. Groups, also called families, are columns on the periodic table. As you can see up here, columns. And they share chemical properties within the column. And periods are rows on the periodic table. And the chemical properties vary across the periods. As you can see, rows. Groups are columns, periods are rows. Again, groups, columns, periods, rows. Now, elements can be classified as metals, nonmetals, metalloids, and noble gases. Metals are shiny, malleable, they can be hammered into thin sheets, ductile, drawn into wire, and are defined as good conductors of heat and electricity, and most are solid at room temperature. These all metals here in blue, except hydrogen up there. Don't think of hydrogen as a metal. It's not. It never is. It will never be a metal. Hydrogen. Non-metals are gases mostly at room temperature. However, solid non-metals include carbon and sulfur. Solid non-metals are brittle and poor conductors of heat and electricity. They include hydrogen, helium on down, carbon, and all those in orange. Metalloids are elements that have some characteristics of metals and some characteristics of non-metals. It's in between. They all are solids at room temperature. They are less malleable than metals, but not as brittle as non-metals. They're semiconductors of electricity used in computers, TVs, and radios. You can find the metalloids right over here, and there's usually a staircase down the middle of the periodic table right there, and these are the metalloids. And then you have noble gases. They are in group 18 of the periodic table, and they are unreactive. They are gases room temperature, They're used in lighting, neon lighting, and in party and weather balloons, helium. And as you can see right here in green, helium, neon, argon, krypton, xenon, and radon will never get